is. Okay. I want to say before I start that I've had just a fabulous visit here. It's so impressive, everything that you all are doing. And I'll touch on some of it in my talk itself, but to meet everybody and to see the facilities that I've heard about for such a long time has made for a very, very satisfactory visit. What I'm going to talk about today is bright electron beams for science and society. And to jump in just a little bit, I'm talking about particle accelerators here. And I'm looking around the room and I realize most of you live and breathe particle accelerators, but maybe not everybody. And so here's just a sample of particle accelerators. And you can see they range from synchrotron sources to this is an X-ray source, very huge at SLAC, an electron diffraction lab at Berkeley, the Large Hadron Collider. Here's a miniature accelerator, that's an electron microscope. And then there are even cancer treatment facilities around the world. So when I talk about particle accelerators, I'm really talking about all of these things and more. They matter a lot. They're used widely in industry, for example, food and product safety to make your hamburger safer to eat. They're used in contraband detection, as in this truck where you can see the contents. So at our borders, they're used in polymer cross-linking. That's important for tire manufacturing and for heat shrink tubing, for example, and then semiconductor fabrication. And I'll come back to some of those later on. They're used in medicine, both for isotope production and to treat tumors, particularly tumors that are in sensitive locations, like tumors of the eye, where you don't want to damage nearby brain material. So in all, there are about 40,000 particle accelerators in operation today, and that number is growing fast. In this room, we're mostly used to particle accelerators for research. And they're the big ones, the large X-ray sources, and also the particle colliders. And those have had a huge impact. They're responsible for 1 in 3 Nobel Prizes in both physics and chemistry. And then there are also the smaller ones, the electron microscopes, which are so incredibly important today. So when I look forward to what we can see for the future for particle accelerators, I imagine things like this. I imagine bright beams that reveal not only the structure of biological molecules, but also reveal their function. This is an image of the rhodopsin protein, which is light sensitive. It's in your eye. A state-of-the-art fast electron source would give you an image like that. In other words, you can't see a damn thing. Whereas with 100 times brighter electron beam, the structure would drop out, and then you can actually see it in action. I imagine bright beams that tell us how the proton gets its spin. For example, right now, Brookhaven National Lab is building an electron-ion collider, which will, in fact, tell us the structure of the proton. With brighter beams, you could get higher luminosity and therefore reveal more detail. I imagine bright beams that enable a more sustainable future. There are ideas now for proton accelerators that primarily transmute nuclear waste into materials that have lifetimes, radioactive lifetimes of maybe 100,000 years, and puts that down to just decades, where we can maybe manage them more sustainably. And there are now pilot projects going on to look at that in Europe, India, and China. I imagine bright electron beams that help us extend Moore's law. We have these days integrated circuit fabs with 5 nanometer structures, and those need extreme UV lithography. And in order to do that sustainably, particle accelerators may also be helpful. I imagine bright beams that bring coherent X-rays to university campuses, notably this one, where you have had are leading the world in terms of making compact X-ray sources that are capable of things like at-a-second coherent diffraction imaging. I imagine bright beams that clean the environment. High power accelerators that you can use, for example, to treat wastewater or exhaust. So it was inspiration by all of those things that led to the formation of this center, the Center for Bright Beams. And our overall goal is to gain the fundamental understanding needed to transform the brightness of electron beams available for all of these purposes. And it's a collaboration of multiple institutions. You see ASU right here. There are other universities and also 3 national labs. And we're all partnering together to do this work. I better tell you what brightness is. And here's a cartoon. Here is a bunch of electrons traveling to the right. They're in a clump. Each little momentum vector of each electron is shown by a little red arrow. This is a low brightness bunch. There aren't all that many electrons. They're kind of far apart. They're going every which way. A high brightness bunch is right here, and you can see they're more aligned, they're more densely packed, and there are more of them. So it's this transformation that we're trying to make. And to be a little more mathematical about it, brightness is defined as the beam current divided by something called the emittance. And emittance is just the product of the size and angular spread of the bunch. It's the phase space occupied by the bunch of electrons. And small emittance is good. You want them to occupy a small region of phase space. So we're going for higher brightness. This is a list of all the collaborators, faculty collaborators that are part of the center. I'm guessing everybody and many people will recognize some of the names, but that very few of you will recognize all of them. And that's because they're drawn from a whole bunch of different fields. In order to do what we wanted to do, we needed an interdisciplinary team. So we have condensed matter physicists, material scientists, surface chemists, as well as accelerator physicists. All of the work that I'll show you today was done by the graduate students and postdocs. So here are some of our current graduate students and postdocs. The ones in red are from here. Here are more and postdocs. So I'm going to show you their work. And of course, we have other students and postdocs who have already graduated, 43 so far in the lifetime of the center, and they're out doing all kinds of wonderful things. This particular slide is color-coded by whether they go on in academia, that's red, industry, that's blue, or national labs, green. So back to brightness. Here on this graph, I've got beam power on the horizontal axis. That's the product of current times the energy of the beam, and inverse emittance on the vertical. So we have more compact beams there. And you can see all these different kinds of accelerators. So electron microscopes have rather low beam power, but very tiny emittance. Then all the way up to colliders occupy the right-hand side. And we've got X-ray FELs here in the middle. All of them want higher brightness, which is basically up and to the right. So what are we tackling? I'm going to tell you a little bit about first the production of the electron beam. So here's a particle accelerator. This one happens to be one called LCLS2. It's an X-ray free electron laser under construction at SLAC near Stanford. So let's look at that electron source. The electrons there are produced through the photoelectric effect. This is the same one you learned about very early in your physics career. And we simply have a photocathode right here. And we shine a laser pulse on it, and out comes a bunch of electrons. That's the process. But the idea here is that by designing the photocathode, we can actually make that process better. So what do we want? We want high brightness. That means we want a lot of current and high collimation. We'd like to do that with high quantum efficiency so that we don't have to blast it with a laser. And we want robustness. We want photocathodes that last a long time because we don't want to be going in and swapping them out all the time. So for high current, you need a strong electric field at the photocathode surface, and we're talking typically about 100 megavolts per meter more. And then you also want high collimation as the electrons emerge. So here's a photocathode, and here there are little velocity, momentum vectors coming off. And there's a component of their velocity that's that's parallel to the surface, perpendicular to the direction we want them to go. And we define something called the mean transverse energy, just 1/2 mv squared, where we're taking the bad component of velocity. And we would like MTE, the mean transverse energy, to be small. And in fact, you can show that the brightness, the thing we're trying to maximize, is just proportional to the electric field divided by the mean transverse energy. At room temperature, you've got thermal mean transverse energy of about 25 millielectron volts. It turns out that typical photocathodes today, like you put up some copper, will operate with more than 300 millielectron volts, so far above what you would expect from thermal effects alone. And the question is, can we do better than that? And so maybe we have to think just a little bit about the photoemission process. And so we have this energy diagram, and here's the photocathode. Energy levels are filled up to the Fermi level. And then to emit an electron, you need to supply a photon that has at least this work function in order to kick the electron out into the vacuum. Now, if the photon has a lot of energy, if you're way much more than the work function, then typically the electron will come out and it will have a bunch of kinetic energy. Typically, some of that is transverse and therefore bad. If you hit the photocathode with photon energy about exactly equal to the work function, then it will come out with very small kinetic energy and tend to have less mean transverse energy. So that suggests an easy way to lower your MTE, increase brightness, and that's to choose the energy of your laser light to be close to the work function. Another thing you can do is cool the photocathode to low temperature, because that reduces this smearing at the Fermi level. There's a penalty for low MTE for hitting things with just exactly the work function, and that's that you tend to have low quantum efficiency. If you hit with a large energy photon, you can hit out electrons from anywhere in here, whereas if you're hitting it with exactly the work function, you really can only access electrons at the Fermi level. So there's a trade-off we can see that we're going to have right there. The record for MTE was done with a cool copper photocathode by Sid Karkare and others, and their data is shown here. So they took clean ordered copper 100, cooled it down to 35K, and there they were able to achieve MTE of 5 millielectron volts, and that holds the record. But as predicted, the quantum efficiency was very, very low. And that's a trade-off you're always going to have with a metal photocathode. So you might say, why not hit it with a lot of laser light, get out a lot of photoelectrons? Who cares if there's a low quantum efficiency? And the reason that's not a good idea is that you can have there's a large photon flux. A single electron can absorb multiple photons, and therefore you get high kinetic energy electrons coming out. And you can see that in this is a theoretical prediction here. At low laser fluence, you have very low mean transverse energy if you hit it exactly with the work function, photons at the work function, and then gradually the MTE increases as you increase the energy. Well, if you have a high laser fluence, then you have very high mean transverse energy, even when you hit it exactly at the work function. And in fact, that's been experimentally demonstrated also here at ASU by graduate student Chris Nill. So for metal photocathodes, MTE and high current, low MTE and high current is not achievable. So what do? We look for semiconductor photocathodes, and here's a sampling of them. You can see there are quite a lot of options. They have high quantum efficiency. Some of them operate in a very appealing range for lasers. And so we'll go there. Here is some data compiled for a lot of these different photocathodes. And you can see, again, this is the excess energy of the photon, the mean transverse energy. One thing you can see, if you zoom in on this region down here, is that you never really get to quite what you think you ought to. You never achieve thermal MTE, even with very low excess energy. And that's not entirely understood. One reason for it may be photocathode surface quality. So here's a photocathode surface made through co-deposition, which is a good method, but you see the bumps on the surface, and what happens is that produces an electric field. Remember, this thing is bathed in a very strong electric field that gives a component parallel to the surface, and that creates large MTE, and it especially gets large if you have a strong electric field, which we do. So one solution is to grow a single crystal photocathode, and in fact, just this past year, that was achieved for the first time, a single crystal semiconductor photocathode with molecular beam epitaxy, and it looks very promising. It's fast, it has high quantum efficiency and low MTE. We don't know about robustness yet. There's work going on to cap photocathodes with graphene layers that looks very promising. In fact, some of that work was done here. So this looks promising, but it's sort of a Maserati of photocathodes, and what makes you wonder, is there an easier way? And so the ASU, some of the work to answer that question is being done here at ASU. Here's the photo emission and bright beams lab that you have, and you can see it. It's an amazing resource with all growth chambers here, and then all kinds of diagnostic equipment here, and finally a DC gun. All of this is operating at 10 to the minus 10 torr, and you can wheel your photocathode around anywhere you want in that entire device. So these are the students who have been doing that work, and let me show you some of their data. Here is a photocathode that was grown through co-deposition, and here they have been able to plot the maximum kinetic energy as a function of the incident photon energy from the laser. And what that shows is that there's the work function for this material, which is one that's been studied a lot, is at about 1.5 electron volts. That's quite a lot lower than previously thought. And it suggests that maybe when people were making the MTE measurements, they were looking out here rather than right at threshold. When they make their MTE measurements going all the way down to this lower threshold, they see 30 millielectron volts, which is within measurement errors of KT. So this is very interesting, and I think still being, it's very exciting to see low MTE at room temperature. It's the first time that's been done. There's the caveat that low quantum efficiency is low, so there's more work to be done, but this is a very exciting advance. I thought I'd show you something with the impact of a good photocathode. This is one that has MTE that's around, I think it's 60 millielectron volts. And this is an ultra-fast electron diffraction pattern. Here, what we've taken is two hexagonal atomic layers and then given them a little twist so that there's both the small scale hexagonal structure, but also a large scale one that comes out, the moire pattern. And if you look at the diffraction pattern from that, you look at one of these bright spots, it has it actually consists of two bright spots. One of those is from each of these two layers, but there are also two little satellite spots, and those come from the very large scale pattern. The hexagonal pattern that's like that. And that's exciting because it requires a very large coherence length for the electron beam, and that's possible only with the good photocathode. And and tuning. So that's a hint of the kinds of things that we can do as these good photocathodes get put to work. They can also have an impact for X-ray FELs. This is a graph that comes from SLAC for their LCLS2 X-ray FEL. This is the X-ray spectrum that they expect from their default design. With a better photocathode and good delivery to the end, they could actually increase the spectrum like that. So it can have very significant influence over the performance of an accelerator. Now I'm going to switch gears a little bit and talk about beam acceleration. So here's LCLS2 again. We did the source. The beam then gets accelerated through here. These are superconducting RF cavities. They're actually at 2 Kelvin, and so they're in a big cryo module. That's what this thing is. And let's look at that. So here is a view of one of those cavities. Looks sort of like an egg carton, except that it's about the size of this table. And inside there are oscillating electric and magnetic fields. The red is the magnetic field, the blue is the electric field. And that electric field is timed in sync with the beam, and it actually accelerates it. The beam sort of surfs along that electric field. And so as you're designing these things, well, I should say these things have enormous quality factors, like a Q of 10 to the 11th. If you think of mechanical resonators, what's a typical Q in a mechanical resonator? Maybe 100. And so the Q of these things is huge. What do you want in them? You want high accelerating gradient, so that you accelerate the beam quickly. You want energy efficiency for obvious reasons, and reliability. So, and I apologize here to the condensed matter physicists. Here's the nutshell superconductivity. But we know that at low temperatures, you get weak attraction between electrons to form Cooper pairs. And then those Cooper pairs form a condensate in the material who doesn't see defects. And as a result, there's zero DC resistance. It turns out, however, that in the presence of oscillating fields, they do have resistance. And BCS theory tells you that that has a functional form like this. It's proportional to the frequency squared. We're typically operating in the gigahertz regime. And then it's also, the resistance goes down exponentially with temperature relative to the critical temperature of the material. And you can see all that here. We're going to lower temperature to the right. You can see this exponential drop in the resistance. And then finally it bottoms out, and there's some additional resistance coming from other sources that we'll talk about in a second. But the bottom line is that you have the resistance has two terms, one of which falls exponentially with temperature and the other residual. Resistance lowers the quality factor of the resonance, it causes heating. And so what we want for good operation is very low temperature and also low residual resistance, or at least we want to operate far below the critical temperature, and we want low residual resistance. So just as a reminder of the phase diagram, here's the temperature of a type 2 superconductor, and we're talking typically about niobium, and versus the magnetic field. Down at very low magnetic fields, you're in the Meissner state where you exclude magnetic fields from the interior of the metal. At higher magnetic fields or higher temperatures, of course, the magnetic field it goes in the metal. In between, you have this vortex state. A vortex is just a normal conducting core surrounded by supercurrents. And in the vortex state, vortices can penetrate into your superconductor. Vortices are bad because they cause heating. In the presence of the AC field, your vortices are going back and forth like that. That's heating. It turns out there's a metastable state where vortex entry is technically allowed, but preventable. This is sort of like supersaturation of a cloud with water. So in reality, superconducting RF cavities operate inside this metastable state. We need to keep the field, the magnetic field, below this superheating critical field here so that we don't enter the vortex state. So the main goals are to stay there and to minimize vortex entry. And I should say, the reason this superheating critical field matters is because the electric field that you sustain in the cavity is proportional to the magnetic field. So if there's a limit to the magnetic field, there's also a limit to the electric field. But the electric field is the thing that's doing the accelerating. So you would like that to be large, but you're limited by the superheating critical field here. Okay, why does it turns out operating temperature matters a lot. Each superconducting RF cavity produces about 10 watts. That's like a Christmas tree light bulb, the old-fashioned incandescent kind. But you have 280 of those, and you need to cool them. To do that takes an engine and a cryo plant. And so there's a coefficient of performance of 800 at 2 Kelvin. So in order to cool down this 10 watts that's being produced by each cavity, you need these cryo plants. LCLS2 has 2 of them. Each one uses megawatts of power and costs around $100 million. So this is a significant cost driver for large-scale particle accelerators. And so for this reason, there's a strong incentive to try and operate at higher temperatures. And I'm going to be talking about operating up here where the cryo plant may not be necessary. So we're trying to think about other materials that could work, and the leading contender and alternatives to niobium. And the leading contender is niobium-3 tin. And there are a couple of reasons. One is that it allows potentially for a higher accelerating gradient, a higher accelerating field. And that's because the superheating critical field is higher. So here's niobium, there's niobium-3 tin. The accelerating gradient's proportional to that. And so it's about twice as high in niobium-3 tin as in niobium. And that means you can have an particle accelerator that's half as long. You also want lower cooling cost. And so for that means you want a higher critical temperature. And that critical temperature for niobium-3 tin is about twice as high as the critical temperature for niobium. And so that means that you can get higher Q. And maybe most interesting is that you can get about the same Q quality factor at 4.2 Kelvin for niobium-3 tin that you would at 2 Kelvin for niobium. So that's a big win in cooling costs. So people have been trying this for a while. So back in the mid-90s, here's the accelerating gradient and the quality factor. And it looks really great when the quality factor is, when the accelerating gradient is low. But when people tried to push the accelerating gradient, the quality factor, the resistance was going way up. Nobody understood. It looked horrible. There are other problems. Niobium-3 tin is super brittle. You can machine niobium, but there's no way you can machine niobium-3 tin. Instead, people talk about coating it. The fields don't penetrate very deep inside a superconductor. It's maybe 100 nanometers. So you only really need, microns of thickness to get the performance. Then it has very poor thermal conductivity. I'll come back to that. That turns out to be a problem. It has small coherence length. That means that you're going to be very sensitive to small defects. And finally, the critical temperature turns out to be very sensitive to the concentration of tin, whether it's really niobium-3 tin or niobium, or something a little off from that. And so let's look at that. So here's one problem is having too little tin. So here's the niobium-3 tin structure. And this is what you want. You want 25% tin, but very often tin likes to substitute for one of the, niobium substitutes for one of the tin. And that doesn't have to happen very often to totally blow the performance. And we've done lots of density functional theory calculations to understand this effect. Bottom line is that you need 24 to 25% tin to get the performance. Oops. And if you look at surfaces that you prepare, we found that initially we had lots of depleted regions. That was really bad. And we used a density functional theory to understand the growth process, how the tin was migrating through the niobium. And that led to changes in our growth. And that has now solved this problem. We now are able to produce good niobium-3 tin surfaces or without these kinds of depletion regions. And the result of that is that here's now the quality factor versus the accelerating gradient. And for niobium and for niobium-3 tin, this is at 4.2 Kelvin, and niobium-3 tin beats niobium by a very large factor. It's it's 20 times more efficient than niobium. So all of this bodes well, but there are problems still. One is surface roughness. Niobium-3 tin surfaces, when you look at them closely, look like this. They're quite rough. And that means that locally, the magnetic field can go higher than what it is on average. And remember, we're very limited, our accelerating gradient is limited by that. Also, the divots let vortices enter the body of the material. And here's a little simulation that we've done of that. Oops. Oh. So this is niobium-3 tin at one of those grain boundaries, and you're going to see vortices enter. There's an external magnetic field here. Yeah. So there are vortices coming into the material, and then bang, they go out into the bulk. And now those things are free to oscillate and cause heating. So this is a big problem. It turns out we need a smooth surface in order to prevent this from happening. Another problem that we have is heat dissipation. I said that thermal conductivity was low. So if you have just a small amount of heat, everything is a hot spot on the surface, it can be okay. But if it gets above a certain threshold, then it spreads, and oh God, and the whole cavity quenches. And of course, that then takes a lot of recovery. And so we need to prevent that, which means that we need to prevent the quench. And the way to do that is to use thinner layers of niobium-3 tin. It does not conduct the heat away well, but niobium does. And so if this layer is thinner, you can you can absorb the heat before it causes a quench. So that's the main area of research in niobium-3 tin today, is to make thin, smooth layers. Nevertheless, the progress has been enough, as I showed you earlier, that this technology is being developed very rapidly in a number of labs. Already, by being able to operate at 4 Kelvin rather than 2 Kelvin, we get rid of this whole cryo plant. We can just use a little cryo cooler. It's about it reduces the cost from about 1 million to about $50K. Much more affordable. So we're on the brink of something where this very beautiful kind of acceleration can be used, in basements, in industry, and so on, because a lot of the technical obstacles are being overcome. So why do some of these things matter? What time is it? 4:07. Yeah. So one reason it matters is precision lithography. I mentioned earlier that we want, say, 5 nanometer feature size on chips. You want that to be able to have smaller iPhones and stuff like that. And in order to do that, you need extreme UV light, and that's important for economic competitiveness. In order to do that, today's EUV tools vaporize tin they use a laser to produce a tin plasma that then has transitions that are in the right wavelength. And you can see, this is a graph that shows the number of these EUV tools in operation. This is from 2017, there were none, to 2023, where we've got hundreds of them in operation. And the number is exploding. And the challenge here, these are complicated, they're expensive, but maybe most critical, they use a lot of energy, 1 to 2 megawatts for each one of these tools. So this is now starting to have a big footprint. The Taiwan Semiconductor Manufacturing Company, which is the world's biggest supplier of integrated circuits, now uses 6% of the electricity in Taiwan. And the projection is that by 2025, they're going to be using 12.5% of the electricity in Taiwan. These are enormous numbers. And that's just it's only going to grow beyond this. So is there a different way? And the answer is there may be. There are designs now for EUV lithography that is done using a particle accelerator. You won't be surprised. And let me just walk you through this. This is a gun, like the ones I showed you where you produce an electron beam. It's then accelerated through superconducting or through cavities up to speed. It comes around corner. These are undulators that cause the electrons to jiggle and produce extreme UV radiation. That's then sent out into the rest of the fab for semiconductor manufacturing. The spent beam, after it does its radiating, comes back around and that energy is recycled. So this has a bunch of advantages. You get very high EUV power that actually can increase the quality of the lithography. Fewer defects. It's upgradable, and you could change the energy here when you want to go to even smaller feature size. Polarization turns out to be useful, and overall there's about 10 times better energy efficiency per wafer than with the technology that's in use today. So this is extremely exciting. There are 2 US startup companies that I'm aware of that are trying to bring this technology to market. One of them is X-Light, and many of our collaborators are involved in that. So hopefully this technology will be put to use. What about this? Do you know what these are? Anybody know what these things are? What? Worms? Tapeworm, good guess. It's a roundworm. They're roundworms. And they're found in human intestines worldwide. About 22% of humans have them. In the US, it's about 2%. And they're in your intestines, and they get passed out through feces, and they go into the sewage system. And so what happens to them in our sewage system? They cause illness. They cause things like malnutrition for people who suffer from them. So here's a sewage treatment plant. Sewage comes in here. It goes into something called an aerator, and the first few steps separates relatively clean water from sludge. The sludge goes into something called a digester, where anaerobic digestion happens, and that takes maybe a month, 20 days. And out of that comes 2 things. One, there's biogas and so on that that's processed. Another thing is compost. So this is solid waste that is produced at the end. I call it compost, but it's low-grade compost. And the reason for that is that it still has all those parasite eggs, not just roundworms, but everything else too. And so it's not, you can't use that compost on food crops, for example. You could do it on use it on non-food crops. So that's a problem. But what you can do is use a high power electron beam right here. And what that does is it kills the pathogens. It inactivates the parasite ova, it breaks down pharmaceuticals, and it produces fertilizer that we believe is microbiologically safe. So this is a pretty exciting thing, and there are pilot plants under construction in Poland and China to try this approach. It's one of the many uses of, for example, of the kinds of beams I've been showing you. So I'm sort of going to wrap up here. I've shown you photocathodes that are demonstrating 30 times better performance than copper and good and improving robustness, that are enabling things like ultra-fast electron diffraction and could be used in X-ray FELs. I haven't shown you so much, but we've optimized beam lines that deliver bright beams to the target for X-ray FELs, colliders, ultra-fast electron diffraction, and I haven't shown it to you, but we're doing real-time tuning of electron microscopes. There's cheap acceleration for high power beams, like the ones needed to treat sludge using niobium-3 tin. Those could also be used, for example, in the EUV lithography. And we have produced a team that's interdisciplinary, spans the country, and yet is incredibly cohesive and has done all this work. And most of all, we have 43 fantastic scientists with high demand skills. So this is the future. This is what bright beams will enable. It's a snapshot. I maybe electron microscopy and electron diffraction with real-time tuning for better imaging at the atomic scale, colliders with higher luminosity, cheaper acceleration for bigger scientific reach, X-ray FELs and brighter electron beams, both large-scale ones and compact ones, like the ones you guys are so impressively building here, and new turnkey high superconducting RF accelerators that can produce high power beams for innovation in industry and waste treatment. So thank you very much.